Here's another example of being able to use a linear approximating polynomial and a quadratic approximating polynomial to be able to approximate the value of a not so nice function or a not so nice expression. So we're going to have this function f of x equals 1 over 1 plus x, or 1 minus x, excuse me, centered about the point a equals 0 to approximate 1 over this 0.91. All right, so the first thing we're going to do with this, unlike the previous problem, is we're going to find out what x is. Now we know a is 0, so that's easy. But what we're going to do is we're going to set 1 minus x equal to 0.91. Right? Because that's going to be the value that we plug in for each of our for each of these approximating polynomials. If we solve this, we're going to subtract 1 from both sides, right? And so that's going to give us that x is going to be 0.09. So we're going to hold on to that, and we're going to hold on to a equals 0. Backing up a moment to the previous problem, notice that we didn't solve anything because there was nothing to solve. All right, because whatever was under the radical was going to be x. But if it were like x minus 1 or x plus 2 or something like that, then we would have to do the process that we just did and solve for whatever value we're going to substitute for x. Definitions of our polynomials. Remember, p sub 1 of x, our linear polynomial, is going to be f at a plus f prime at a, x minus a. And then for p sub 2 of x, that's the exact same thing as p sub 1, except we're going to add the second derivative of a over 2, x minus a squared, right? And remember that a equals 0, so that's actually going to make this pretty easy when we find both. All right, so let's go ahead first and find what the interpolating polynomials are by finding the successive derivatives of the original function. One thing to keep in mind is that we can rewrite the original function as 1 minus x to the minus 1 power. Okay, so let's just rewrite f of x as 1 minus x to the minus 1. Right? If we go through and find our derivatives, that means that f prime of x is going to be equal to negative 1, 1 minus x to the minus 2, and then we have a chain rule where we're going to multiply by the derivative of the inside, which is negative 1, right? Now, for this first one, that's going to be equal to 1 over 1 minus x, which was the original. For the second one, we could either write this as 1 minus x to the minus 2, or we could write this as 1 over 1 minus x squared. Now, this is going to be more useful for us as we substitute a back in. This is going to be more useful for when we find the second derivative, okay? Because if you look at our p sub 2, we do need the second derivative, okay? So next thing we're going to do is we're going to find the second derivative. We're just going to take the derivative of this. So that's going to be negative 2, 1 minus x to the minus 3 power, and then we have another negative 1 in there. All right. So if I multiply the negative 1 and the negative 2 out, two ways of writing this: 2, 1 minus x to the minus 3, or 2 over 1 minus x cubed. All right. So these are, and I'm going to box these because these are going to be the most important ones. These are going to be our 0th, first, and second derivative. Now remember, according to our formula, we need to find at a. So we're just going to substitute a back in for each of those. Okay, so if we were to substitute 0 back in, well, that's a 1 over 1 minus 0, which is 1. Okay, so that's our f at a, okay, which is going to be f at 0, since a is equal to 0. I'll just use a. Okay, so f at a is 1. This is going to be f prime at a, and remember a is 0, so that's 1 over 1 minus 0 squared, or that's going to be 1. Okay, so let's hold on to these. And then finally, over here, if we substitute 0 back in, f double prime at 0, that's going to be 2 over 1 minus 0 cubed, which is going to be 2. All right, so we're going to hold on to these values because these are important for us to be able to find our polynomials. So now let's find P1 and P2. All right, so for I, P sub 1 of x is going to be equal to, now we have our formula up here. That's f of a plus f prime of a, x minus a. And remember, a is 0, and we have 1 and 1 for f of a and f prime of a respectively. So we can write this as 1 plus 1 times x minus 0, and that's going to be the same thing as 1 plus x. For p sub 2 of x, that's going to be equal to what we just got. So 1 plus x plus, and if we look at the rest of it, we have the second derivative of a divided by 2, and then x minus a squared. Okay, so this is going to be 2 over 2 x minus 0 squared. That just becomes a 1, and then that becomes x squared. So p sub 2 is going to be 1 plus x squared. So these are our two approximating polynomials. And remember, the whole purpose is to be able to approximate 1 over 0.91. And remember, we said that, okay, well, the distance is going to be 0.09, okay, if we're centering it about the origin, a equals 0. So this is what we're going to plug in for x, all right? And it's actually pretty easy to compute both P1 and P2, all right? So P sub 1 at 0.09 is going to be equal to 1 plus x, or 1 plus 0.09, which is going to be 1.09. All right, that was an easy one to figure out. That's why we like local linear approximations, because they're usually really easy. P sub 2 of 0.09 is going to be equal to 1 plus 0.09, which was x, plus 0.09 squared. All right, and if I just go through and substitute that back in to our calculator, so we have 1 plus 0.09 plus 0.09 square. All right, that gives us 1.0981. Okay, so 1.0981. Now, let's see how close these really are. Okay, so if I throw in my calculator, and again, I didn't ask you to do this, and the directions didn't ask you to do it, but let's just figure out if we're anywhere in the neighborhood of this. So in my calculator, I'm going to substitute back in 1 over 0.91, and notice what we get, 1.098901 if we wanted to go ahead and expand it. So 1.098901. All right. And that's pretty close. All right. So notice that we're accurate up to the thousandths place with P2. We're accurate to the hundredths place on P sub 1. All right. So it looks like that both of those are decent approximations, considering that we didn't have to go through and do long division to figure this out. Okay. So that's where we're going to use these polynomial sorts of approximating these polynomial approximations. Now, in the next videos, what we're going to look at is we're going to look at how do we get higher degrees than just quadratics. Okay, so we're going to be looking at third, fourth, fifth degree polynomials from our power series.